So welcome, Afra. Welcome, Safa. Welcome, Herman. Let's get going. Continuing our conversation about sequences. We're taking a nice little break from like some more hardcore proof techniques like contradiction and contrapositive. And now we're talking about sequences, but don't worry. The only reason we're talking about sequences is because it's eventually going to lead to...
Professor, I had a question.
Yeah, what's up? What's up?
I was going through the homepage of our course on Canvas, and I cannot get access to written assignment 9. It says closed till November 1st, but it's due on October 13th.
That's an issue, isn't it? Wait 1 second. Thank you, Safa. Or thank you, Afra. I will do that. I will do that. I will get you that right after class. Do not worry about that unless it does not click the publish button. That's okay. We'll fix it. Thank you, though. But actually, I'll write that down. Okay. But anyway, the sequences. So like I said, we were talking about contrapositive, contradiction, and direct proofs. We're past that. Now we're talking about sequences because it will lead to something called mathematical induction, which is a way that we can prove things that we've never been able to prove before. In fact, one thing it allows us to prove is a little ditty called Euler's formula, actually Euler's criterion, which goes like this. I don't know if you've ever seen this before. Have you ever, if you look at, oh, I actually have them. If you look at a cube, right? A cube has how many faces? It has 1, 2, 3, 4, 5, 6 faces. So a cube has 6 faces. How many edges does it have? Well, it has 1, 2, 3, 4, 5, 6, 7, 8 edges. And how many vertices is it? Like how many corners does it have? And it has 1, 2, 3, 4, 5, 6, 7, 8 corners. So vertices, edges, and faces. And actually it's edges I got wrong because I forgot 4. There's 1, 2, 3, 4, 5, 6, 7, 8 edges in the top and the bottom, but don't forget the ones in the middle. There's 1, 2, 3, 4 more in the middle. There's actually 12 edges in the middle. The point is, for a cube, this is going to feel arbitrary. If you take its number of vertices minus the number of edges plus the number of faces, you get 8 minus 12 plus 6, which is minus 4 plus 6, which is 2 for a cube. Let's take like a tetrahedron, which looks like this, right triangles on all sides. The number of vertices is so for a tetrahedron, the number of vertices is 1, 2, 3, 4. The number of edges is 1, 2, 3, 4, 5, 6. The number of faces is 1, 2, 3, 4. Yeah, this is gonna get us 4 minus 6 minus 2 plus 4 is 2. This actually works if you just draw like anything. You just draw like anything like right here. If you take this thing right here, this weird shape, doesn't even matter what it represents. This has how many faces? Well, actually, let's do. The point, I'm getting way off topic. The point is, it always equals 2. No matter what 3D polyhedra you pick, it could be a pyramid. It doesn't have to be a regular one. It could be a pyramid. It could be like a soccer ball shape, icosahedron, tetrahedron, any one of those D&D dice, if you're like me. All of those, if you take their number of vertices minus the number of edges plus the number of faces, it's always going to equal 2. Always. Natural question is why? Why the hell would all of these shapes are totally different, right? All of this weird invariance. If you take their number of vertices minus edges plus faces equals 2. And the question is, how would you ever even begin to prove that? With the methods we have so far, basically impossible. Like direct proof, like where to even start? Contrapositive, what's it even mean? Right? Like contradiction, it's hard. But induction is going to allow us to prove this actually kind of easy. So anyway, that's what we're looking forward to. But in order to get to that, we need to first talk about sequences. Let me get John Oliver back in place. There we go. So first talk about sequences. So we're on section 5.1/5.6, and that's weird. The book skips around. 5.1 is sequences, 5.6 is recursive sequences. We're going to do them at once. And it's all about sequences. So let's just remind ourselves what a sequence even is. A sequence is something that kind of goes like this, where you have just a sequence, mathematical sequence, a sequence of numbers. It goes like AM plus 1, AM plus 2, and it keeps going till you get to AN minus 1, and you finally get to AN. And all these AI here, all of these A's, they all represent numbers. So a sequence is just, well, a sequence of numbers, right? It's just kind of a list of numbers like we talked about last time. An example being, we could have 0, 2, 4, 6, 8, 10, something like that. Now, one way that we can describe our sequence here is we could say, instead of saying, well, like all of this, or sorry. One way, so one way we can write this shorthand, well, sorry, we'll get to that. So this is a sequence. And one way we can write it is like this. We can write this as, consider this the sequence of all AI, where AI here is going to equal 2 times I for all I greater than or equal to 0. So, I'm sorry. For all I greater than or equal to 0 and I less than or equal to 5. In this particular case. Why is that? Why is this saying the same thing as this? Well, because if we actually start to write this out, right, we get, well, I has to be between 0 and 5. So really we could write this as for all 0 less than or equal to I less than or equal to 5. So if we actually start to write it out, we go, okay, our I is going to range between 0 and 5 as integers, right? And so we're going to start with A0, A1, A2, A3, A4, and go all the way up to A5. Now, A0 is supposed to be 2 times 0 if we follow this formula, right? A0 is 2 times 0. This is 2 times 0, which is 0. A1 is 2 times 1, which is 2. A2 is 2 times 2, which is 4. A3 is 2 times 3, which is 6. A4 is 2 times 4, which is 8. And A5 is 2 times 5, which equals 10. Am I off the screen? And so we get 0, 2, 4, 6, 8, 10. The point being that this right here and this right here represent the exact same sequence, right? It's kind of written in 2 different ways. This is kind of like a more compact way to write this sequence right here. Now you might say, well, why would I ever use this form in red over this form in blue? Like this form in blue seems like the more natural way to write the sequence. Well, the reason is, what if we're talking about sequences that have 1 million values? well, then do we really want to write down all the million values, or do we just want to write down what it equals and then say the range? I would rather say what it equals in the range. Or even beyond a million, what if it's infinite? For example, what if instead of it ending at 10, the sequence just kept going? Right? It went to 12, 14, but it never stopped. It went on and on and on. If it was an infinite sequence. Well, then the way you represent that is that you still have AI equals 2 times I, right? It's still the same pattern, but it just doesn't stop. So it's just for all I greater than or equal to 0 now. Does that make sense? All we're talking about here is this is a different way to represent sequences rather than just writing them out. And this is called its explicit form.